Weak acids and ionization constants. Okay, so ionization constant is just an equilibrium constant when an acid dissociates in water to produce H plus ions. So well, there it is, an acid ionization constant is a particular kind of equilibrium constant, right? So when I put generic acid into water and it protonates water to form hydronium ion, this is the definition of what we call a Ka, a acid-base ionization constant. So again, we leave water out of the equilibrium expression because so little water is involved in the reaction. We couldn't include the water in the solution, right? So again, all solvents are left out, all liquids. The only thing that's included in equilibrium expression are things that are dissolved in water or gases. So the natural definition that we use when we talk about Kas is the Arrhenius definition. HA breaking apart to form H plus ion and some sort of conjugate base. Acid ionization constant. All right, ionization constants of some weak acids at 25 degrees Celsius. So all equilibrium constants are temperature dependent. Hydrofluoric acid at 25 degrees Celsius has a Ka of 1.7 times 10 to the minus 4. So like all weak acids, this is reactant favored, meaning this doesn't go very far forward before the reverse reaction takes over and H plus protonates fluoride ion again to reform the acid. So if I have a weak acid, I have a decent conjugate base. Fluoride ion is a base. It will take an H. So this reaction stops because fluoride ion is a decent base. It'll take an H plus. Nonetheless, it's got a very small Kb value, right? 1.4 times 10 to the minus. No. I'm sorry. Gosh, I made a total mistake. It's easy to do. A Kb value is something different than the reverse reaction. A Kb value is going to be about fluoride ion reacting with water. So it's a measure of how strong a base is. So if I have a Ka value of 10 to the negative 4, its conjugate base has a Kb value of 10 to the negative 11. This is a measure of what kind of a base fluoride ion is in terms of reacting with water to produce hydroxide. Comparing the two, right? If we have hydrofluoric acid with a Ka of 10 to the negative 4, the Ka for hydrocyanic acid is 10 to the negative 10. So hydrocyanic acid is a much weaker acid, or not much weaker acid than hydrofluoric acid. So there are degrees of being a weaker acid depending on your Ka. So if you have a really small Ka, right, you're a really lousy acid, that makes you even more significant base. So a Kb value for cyanide ion of 10 to the negative 4. So weak acid, strong conjugate base. Ka of 10 to the negative 5. So acetate would have a Kb value of 10 to the negative 10. So you can kind of see a pattern here, right? 10 to the negative 5, 10 to the negative 10. So the stronger the weak acid, the smaller its conjugate base. Nonetheless, acetate is a significant base. All right, what is the pH of a 0.122 molar solution of weak monoprotic acid with a Ka of 5.7 times 10 to the negative 4? So we're just solving for equilibrium concentration here, right? We have the equilibrium concentration of the H plus ion. We can take the negative log and get the pH. So I'm starting with a 0.122 molar weak acid. I recognize this isn't going very far forward, so we'll say the amount of HA we're losing is small, right? We're going to call it X. So for every X amount of HA lost, I'm making X amount of H plus ion and X amount of its conjugate base. So these would be the equilibrium concentrations, right? 1.22 minus X would represent the change in concentration of the weak acid, and X represents the concentration of H plus, and X represents the concentration of the conjugate base. So I take these equilibrium concentrations, plug them into the Ka expression, set them equal to the Ka value, and solve for X. X will be equal to the H plus concentration. So hey, this is a very small K value, right? 10 to the negative 4. And since the concentration is relatively large compared to that very small K value, I can ignore the change in the concentration of the weak acid, right? I mean, the amount of X you're losing here is insignificant. So it makes it easier to solve. So as long as the Ka is small, I can ignore the change, the change in the initial concentration of the hydrofluoric acid. So multiply both sides by 1.22, take the square root of both sides, and I can solve for X. So I get, very quickly, easily, math-wise, what X is, and I get the H plus concentration. That's what X is equal to. Take the negative log of X, and I get the pH of 2.1. All right, percent ionization is just another way of showing how strong a weak acid is. All right, so the way you calculate the percent ionization is you take the equilibrium concentration of the conjugate base and divide it by the original concentration of the weak acid, multiply by 100, and you get, how much this weak acid ionized. So if we have a 1 molar acetic acid solution, Ka 1.8 times 10 to the negative 5, again, it's weak acid, so it's not going very far forward. So if I'm starting out with a 1 molar concentration, I'm not losing very much of it. We'll call it X. For every X amount of acetic acid lost, I'm making X amount of H plus ion, X amount of acetate. So subtract X from 1 molar. X is equal to the H plus concentration in the acetate concentration, so plug them into the Ka expression and solve for X. We have a very small Ka value and a very high concentration, so I can ignore the change in the original concentration. Again, this makes it easy to solve for, so multiply both sides by 1, take the square root of both sides, and I get X. All right, so X is equal to the conjugate base concentration, acetate. Divide that by the original concentration, 1, multiply by 100, and we get a percent ionization of 0.42%. So again, it's another way of showing how strong this acid is. What's its percent ionization? All right, percent ionization gets greater the more dilute the solution. So, for example, with a 1 molar solution as opposed to a 0.1 molar solution, when you look at the percent ionization, it's greater with the 0.1 molar solution. And the way you can look at this is it's like Le Chatelier's principle. You are diluting the solution. So the solution responds to try to increase that concentration, right? So if you lower the concentration, the system responds to try to replace the concentration. All right, weak bases and base ionization constants, Kb values. So this is a measure of how strong a base is. All right, so we have a weak base. So just like Ka values, these are less than 1. All right, so these are weak bases. So I have some sort of anion that is the conjugate of a weak acid. So how much does it react with water to produce hydroxide, right? Water is going to be the acid. It's going to protonate that anion and produce hydroxide. So again, we leave water out of the solution, even though it's acting with the acid here. It's the solvent. So it's the conjugate acid concentration times the hydroxide concentration divided by the concentration of the weak acid, raise their stoichiometric coefficients. You could also have a neutral base. The only one we know is ammonia. Solved the same way. So ammonia gets protonated by water to form ammonium ion and hydroxide. So if I want to solve for the hydroxide concentration, I would lose a certain amount of ammonia, produce a certain amount of ammonium ion and hydroxide, and I'd plug those, I'd solve for X, right? And I'd solve for the hydroxide concentration. Methylamine. All right, so methylamine will act like a base, right? So just like, almost like, think of it like you've got an ammonia, except you've attached it to a methyl group. So amines are bases. So an H will protonate methylamine to form a cation, and the H comes off of water to form hydroxide. So there's a Kb value of 4.4 times 10 to the negative 4. ethylamine. So we're just putting more methyl groups on it, right? So ethylamine, again, a similar Kb value. And the conjugate acid would have an H plus ion added to the neutral base, right? So we'd have some sort of cation. Again, this pattern, right? If you've got a Kb value of 10 to the negative 4, you've got a Ka value of 10 to the negative almost 10. So there's a relationship here. All right, so this would be the problem. What is the pH of a 0.4 molar ammonia solution? You've got the Kb value. So I've got 0.4 molar as my initial concentration. I'm going to lose X amount of ammonia, make X amount of the conjugate acid, and X amount of hydroxide. So plug into the equilibrium expression, right, these equilibrium concentrations. Solve for X. Again, X is going to be insignificant compared to my initial concentration, so I can ignore the change. So 0.4 multiplied by both sides, take the square root of both sides, and you solve for X. Now, X I've solved for the hydroxide concentration, right? And you're asking for the pH. So two ways to do this, right? I could take the negative log of the OH concentration and subtract from 14, or I could set the X times the hydroxide concentration equal to 10 to the negative 14, solve for the H plus concentration, and then take the negative log to get the pH. I went this route, right? So take the negative log of the OH concentration, get the pOH, subtract from 14 to get the pH. So with a high hydroxide concentration, you have a low H plus concentration. All right, so like we've been alluding to, there's a relationship between the Ka value for a weak acid and the Kb value for its conjugate base. So this is a Ka expression. Again, make sure you understand what a Ka is. This is the hardest thing for students. All it means is how much an acid ionizes in water to produce H plus ion. A Kb value is how much a weak base gets protonated by water to form hydroxide ion. So a lot of people get confused. They think the Kb value is the inverse or the reverse of a Ka expression. No, that's the reverse of a Ka expression. So a Kb value is something very specific. When you put it in water, water protonates the weak acid to form hydroxide. So when I multiply a Ka value by a Kb value, it's equal to Kw, 10 to the negative 14. That's the relationship. So as one value gets very large, the other value has to get very small if it's going to be equal to 10 to the negative 14. So why is this the case? Well, because if you add a Ka expression to a Kb expression, the weak acid cancels out, the weak base cancels out, and you're left with the autoionization of water, Kw. So when we add equilibrium expressions together, we multiply their K values. So Ka times Kb is equal to Kw. So with a large, well, we have a small Ka value, we have a larger Kb value. So the stronger the acid, the weaker the conjugate base. If we have a strong base, the weaker the conjugate acid, and so on. So as one value gets bigger, the other value has to get smaller if it's going to be equal to 10 to the negative 14. So some representative Ka and Kb values, right? So hydrofluoric acid is 7.1 times 10 to the negative 4. So its conjugate base, fluoride ion, would have a very small Kb value, right? 10 to the negative 11. If we look at ammonium ion, right, with a Ka value of 10 to the negative 10, its Kb value is, the Kb value of ammonia is going to be bigger, right? Close to 10 to the negative 4. So these are just some more values, right, off of out of our book. Now here's some variants. So here's chlorous acid, its conjugate base. So chlorous acid has a Ka value of 10 to the negative 2. So that's a fairly significant weak acid, right? 10 to the negative 2 is a big Ka value for these weak acids. So that would mean chlorite would have a very low Kb value, whereas phenol has a very low Ka value, so its conjugate base would be significant, really significant, right? 10 to the negative 4 in that range. Oh, there they are. Okay.